The physical limit of wheeled transport is rolling friction. Maglev systems bypass this constraint entirely by maintaining a non-contact gap between the vehicle and the guideway structure. This levitation relies exclusively on controlled electromagnetic forces interacting between coils on the train and the track. These forces must precisely counteract the gravitational load and simultaneously maintain dynamic stability during high-speed motion. Maglev technology is fundamentally categorized into two primary methods based on the force mechanism: electromagnetic suspension, or EMS, which utilizes magnetic attraction, and electrodynamic suspension, or EDS, which utilizes magnetic repulsion. The complete elimination of mechanical contact allows maglev trains to achieve significantly higher operational speeds than any conventional high-speed rail system currently in use. This non-contact mechanism is the engineering foundation enabling speeds exceeding 600 kilometers per hour. Electrodynamic suspension systems, exemplified by the Japanese SC Maglev, utilize powerful superconducting magnets mounted on the train body. These magnets generate extremely strong, persistent magnetic fields without external power input once cooled below their critical temperature. As the train moves above the guideway, the changing magnetic flux cuts across the track's conductive loops. According to Lenz's law, this changing flux induces eddy currents within the track coils. These induced currents immediately create a secondary repulsive magnetic field that opposes the primary field generated by the superconducting magnets. This magnetic opposition generates the necessary lift force. Levitation in EDS is inherently stable because the repulsive force increases if the gap decreases. However, lift only occurs above a critical transition speed, typically exceeding 150 kilometers per hour, necessitating auxiliary wheels for low-speed movement. The operational air gap in EDS is large, typically ranging from 100 to 150 millimeters. Electromagnetic suspension systems, such as the German Transrapid, rely entirely on attractive magnetic forces for levitation. Electromagnets mounted beneath the train wrap around and attract ferromagnetic rails located on the underside of the guideway structure. Maintaining the required small air gap, typically 8 to 15 millimeters, demands continuous active feedback control. Since magnetic attraction is inherently unstable, a smaller gap leads to exponentially stronger attraction. Any disturbance requires immediate correction. High-speed feedback loops constantly monitor the gap using specialized sensors such as eddy current sensors. These loops dynamically adjust the current supplied to the electromagnets thousands of times per second. This precise dynamic adjustment ensures stability and prevents physical contact between the vehicle and the track. Crucially, EMS systems can maintain full levitation even at zero speed, unlike EDS systems. Maglev trains utilize a linear synchronous motor, or LSM, for both propulsion and regenerative braking, eliminating all rotating mechanical components. In this configuration, the guideway functions as the stator, containing three-phase alternating current windings distributed along the track length. The train carries the field magnets, which act as the rotor. Propulsion is achieved by varying the frequency and phase of the alternating current supplied sequentially to the track segments. This creates a traveling magnetic wave that moves along the guideway. The train's powerful magnets lock onto this moving wave, accelerating the vehicle synchronously, without slippage. Precise speed control is maintained by adjusting the frequency of the alternating current power specifically to the track segments directly beneath the train. This segmented power supply minimizes energy loss across the entire track length. Lateral guidance is essential for keeping the train centered above the guideway and managing significant forces encountered during curves. In electromagnetic suspension systems, separate guidance magnets interact with vertical track surfaces. These magnets use attractive forces and active feedback control loops similar to the levitation system to maintain the precise lateral position. Electrodynamic suspension systems inherently provide strong lateral centering stability. This stability arises naturally from the repulsive forces generated by the induced currents. The specific design of the track coils, often configured as figure-8 loops, is engineered to generate powerful restoring forces. If the vehicle displaces laterally, these forces push the train back toward the central line, ensuring passive stability without requiring continuous active power input for guidance. At operational speeds exceeding 400 kilometers per hour, aerodynamic drag becomes the dominant resistive force acting on the vehicle, significantly outweighing magnetic drag. Drag force increases quadratically with velocity. This means that doubling the train speed requires 4 times the power input solely to overcome air resistance. Minimizing the frontal cross-sectional area and optimizing the train's aerodynamic shape are critical design factors for maximizing high-speed energy efficiency. Future concepts propose operating maglev systems in partially evacuated tubes, known as vac trains. By drastically reducing the ambient air density and resistance within the tube, these systems could potentially enable sustained operational speeds above 1,000 kilometers per hour with manageable energy consumption requirements. The Shanghai Maglev, utilizing electromagnetic suspension technology, operates commercially at 431 kilometers per hour, demonstrating high-speed transit viability. The Japanese SC Maglev holds the current world speed record for rail vehicles at 603 kilometers per hour. While levitation requires minimal energy input once the gap is established, the primary energy consumption is dedicated to propulsion against aerodynamic drag. Aerodynamic drag force increases quadratically with velocity. This means that doubling the train's speed requires 4 times the power input solely to air resistance. Minimizing the frontal cross-sectional area and optimizing the train's aerodynamic shape are critical design factors for maximizing high-speed energy efficiency. Future concepts propose operating maglev systems in partially evacuated tubes, known as vac trains. By drastically reducing the ambient air density and resistance within the tube, these systems could potentially enable sustained operational speeds above 1,000 kilometers per hour with manageable energy consumption requirements. The Shanghai Maglev, utilizing electromagnetic suspension technology, operates commercially at 431 kilometers per hour, demonstrating high-speed transit viability. The Japanese SC Maglev holds the current world speed record for rail vehicles at 603 kilometers per hour. While levitation requires minimal energy input once the gap is established, the primary energy consumption is dedicated to propulsion against aerodynamic drag. Additional energy is required for maintaining the cryogenic cooling systems necessary for the superconducting magnets used in electrodynamic suspension. Maglev systems eliminate mechanical wear on all moving parts, resulting in significantly lower long-term maintenance costs compared to conventional high-speed rail. This reduction in operational expenditure helps offset the substantially higher initial infrastructure investment required for the specialized guideway construction.